Mathematics often feels pristine and abstract, but geometry started in the mud. The Nile River flooded every year, wiping out property lines. Egyptians had to invent physical ways to remeasure land to keep society functioning. In the Indus Valley, city planners faced different problems, needing to build on a massive scale. They developed strict geometric ratios, like kilning bricks to exact 4:2:1 proportions, to construct stable, multi-story cities. For centuries, these scattered rules were treated as practical tools. The shift toward proving why these rules worked started in Greece with mathematicians like Thales. Around 300 BCE, a teacher named Euclid collected all this scattered knowledge. He organized it into a single logical sequence called the elements. Geometry didn't fall out of the sky into a classroom. It was built from the ground up, out of absolute necessity, to impose order on a chaotic physical world. To build his system, Euclid had to start at the absolute bottom. He began with a single dimension of reality, the point. From there, the concepts stack. Drag a point, and you get a one-dimensional line. Drag that line, and you create a two-dimensional surface. But Euclid hit a logical wall. If you formally define a part of a line, you have to define area. To define area, you must define another shape, requiring more parts. You end up in an infinite loop of definitions. To break the loop, Euclid did something completely counterintuitive. He decided that some fundamental concepts, like a point, a line, and a plane, would simply be accepted as undefined terms. We rely on our shared intuition to know what they are. By intentionally leaving the bottom layer undefined, we stop the infinite loop. This gives us a solid, unquestionable floor to stand on before building proofs. With the basic terms in place, we need rules. Euclid split his rules into two categories. First are axioms, or common notions. These are universal rules that apply to all types of mathematics, including basic algebra. The second category is postulates. These are specific rules that only apply to geometric shapes and physical space. Let's run through the axioms. Number 1, if two different things are equal to a third thing, they are equal to each other. Numbers 2 and 3, adding equals to equals yields equals, and subtracting equals from equals leaves equals. Number 4, things that overlap perfectly are identical. And number 5, the whole is always greater than any of its individual parts. Notice that none of these require complex calculation. They are basic, self-evident agreements that we have to shake hands on before any real mathematical debate can start. Moving on to the postulates, we get rules for actual construction. Postulates 1 and 2 state that you can draw a straight line between any 2 points, and that a line segment can be extended indefinitely in either direction. Postulate 3 says you can draw a circle with any center and any radius. Postulate 4 says all right angles are equal to one another. Then we reach postulate 5. While the first 4 rules are short and self-evident, this one is a dense paragraph that demands a much more complex geometric setup to function. Here is a visual breakdown of that dense text. Imagine 2 straight lines cut by a third falling line. This creates interior angles on the inside of the intersection. Look at the 2 angles on the left side. What happens if you add those together and the sum is less than 180 degrees? The postulate guarantees that if you extend those 2 lines indefinitely on that specific side, they will eventually cross and intersect. It takes a lot of words to say it, but postulate 5 is the vital geometric engine that lets us map exactly how lines interact in flat space. Now we combine all these pieces. By stacking undefined terms, axioms, and postulates, Euclid used deductive reasoning to prove totally new, complex statements called theorems. Here is a classic example. We have a line segment AC, with a distinct point B placed somewhere in the middle. We need to prove logically that segment AB plus segment BC equals the total segment AC. If we take segment AB and segment BC, lift them up, and drop them back down, they cover the exact distance of line AC perfectly. Because they overlap exactly, we can invoke axiom 4. Things which coincide with one another are equal to one another. That guarantees our statement is true. This is the core of Euclid's logic. By starting from the most basic, universally agreed upon rules, we can lock in the absolute truth of a brand new claim. We have built the house of geometry. We started with the practical history of land measurement. established our base rules with axioms and postulates, and used those to hold up our complex theorems. For your exams, remember the 3 crucial structural load-bearers: the necessity of undefined terms, the less than 180-degree rule for intersecting lines in Postulate 5, and the definition of a theorem as a formally proved statement. By learning Euclid's geometry, you have downloaded a 2,000-year-old operating system for rigorous logical thinking.